we talk about black holes and galaxy mirrors or black holes in galaxies that are not merging, right? And yeah, please, thank you.
Yeah, so thank you to Mar for hosting me. So yeah, I'm Izzy Garland, final year student at Lancaster. Hopefully handing my thesis in March. And yeah, I'm here to talk to you guys today about merger-free coevolution of black holes and their host galaxies. And really, I want to sort of show that this is a vital piece in the puzzle of galaxy evolution as a whole. So I know that not everyone here necessarily works with galaxies, with AGN. So I'm going to start with a very broad introduction, covering sort of what is coevolution, and more importantly, why do we care? I'm then going to move on to sort of my recent work on bar-driven growth, work led by my colleagues at Galaxies. And I'll finish up with what the next steps in the field are, where we can go next with this work. So like I say, starting right at the beginning, especially if you've just come back after summer, galaxy. So as I'm sure you're all aware, a galaxy is composed of stars, gas, dust, dark matter, and a central supermassive black hole, which is the bit we're going to focus on in a bit. Now, broadly, we can decompose galaxy structure into two distinct components. So we've got this disk part, where the orbits of the stars are all very much in the same plane. It's very rotation supported. And we've got the dispersion supported bulge, where the orbits of the stars are a bit more random in orientation, not necessarily all in the same plane. But this little supermassive black hole seems to be able to have an effect on the whole galaxy. So we don't know much about supermassive black holes. There's theories on how they're formed, but we do know they go through phases of rapid growth and accretion, where we call them AGN, active galactic nucleus. And this is where the black hole will gain most of its mass in these phases. Now, the eagle-eyed of you may have noticed that the reference I'm using for this diagram of an AGN is nearly 30 years old. But actually, overall, the picture hasn't changed too much. So we've got the central supermassive black hole in the middle, which is surrounded by an accretion disk where it gets most of its fuel from. And this is further surrounded by this obscuring torus. And the narrow and broadline regions are so-called for the types of emission we see from them. And given that this is not like the same in every direction, depending on which angle we look at it, depends on what we see. So if we're looking down at this angle, we are not looking through the torus. We've got a very unobscured view of the black hole, and we call it a type 1 AGN because we're really inventive. If we happen to be looking through the torus, then we call it a type 2 AGN, and these are much more obscured. We can't really see the broadline region because it's being like absorbed through everything in the torus. And these AGN can exist in galaxies of all morphologies. So anyone who looks at galaxies is very familiar with the Hubble diagram. I've updated it here with modern images because, well, newer images are always prettier. And we can use this to broadly classify galaxy morphology into two distinct categories. So we've got the ellipticals on this side, which are very elliptical in shape, as the name would suggest. They don't have much disk component. They're often very red. And we've got the disk-dominated galaxies on the right. And we can further separate the disk-dominated galaxies into those that do and don't contain a bar. So you can see the bottom galaxies all contain a large-scale bar. SBB is a really nice example of that. And the top ones don't. Now, given that the idea of this Hubble tuning fork is, well, nearly 100 years old, I'm so excited for when I give this seminar in 2 years' time, and I can be like, it is 100 years old. We have since found many things that don't fit on this diagram. And actually, my colleagues at Galaxies, so Galaxies, if you're not aware of it, it's a citizen science program where essentially we show galaxies to members of the public via an online service, and they classify them. And this means we can classify many more galaxies using our citizen volunteers than by a handful of astronomers looking through thousands of galaxies. And there's also a forum where our volunteers can comment on anything they see that's weird. And it means we find lots of strange objects because most objects are being looked at with human eyes that can go, huh, that's odd. And so Keel et al. 2022 got Hubble time to look at a sample of these, what we call zoo gems in greater detail. So I'm showing examples of some of the things we find here, and we go into more information in the paper. The other thing Galaxy Zoo volunteers noticed was that, contrary to what we see on the Hubble diagram, where we've got these red ellipticals and these blue spirals, they actually noticed not just that these red spirals were appearing, which we've known about their existence for a while, but they noticed a lot of them, and they also noticed a lot of blue ellipticals. So if you're not an observer, when we are looking at a galaxy and we want to see its morphology, it's got to be relatively close so we can see it. Otherwise, it just looks like a blob in the sky. And if we've got a blob in the sky, we still want to be able to take a guess at its morphology. And so for many years, we've said, well, that's a red blob. We can assume it's probably an elliptical, or that's a blue blob. It's probably a spiral. But actually, as we showed in Sledis and Masters et al. 2022, red disks and blue ellipticals are common enough that we can't actually use color as a proxy for morphology. And again, you can check out that paper if you want more information. But this is just an example of some of the strange galaxies we found in Galaxy Zoo. But all of these galaxies can host AGN. They can host these supermassive black holes that are growing. Turns out, not only do they host these supermassive black holes, they're co-evolving with them. So I'm showing some relationships here from this review paper, Cormandy and Ho. It's a very good in-depth paper, but it is 137 pages, so read it at your risk. So you've got the black hole mass on the y-axis. On the first x-axis, we've got the luminosity of the bulge, and on the second x-axis, we've got the velocity dispersion within inside the effective radius that encompasses half the light of the bulge. So you can see that we've got the galaxy properties and the black hole properties, and they're co-evolving together. The other relationship that we use that's a little bit older but has sort of become the canonical relationship is this Herring and Ritz relationship. And this is the black hole mass grows with the bulge mass. Now, it's worth noting that this study used ellipticals. So the bulge mass is very similar to the total mass, given that ellipticals have very little disk component. And at first, this seems obvious. Bigger stuff lives in bigger things. But if you look at the scales that we're seeing, the black hole is maybe 1% at best, the stellar mass of the galaxy or the bulge, probably closer to 0.1%. The black hole is also maybe a handful of AU in radius, the galaxy, hundreds of thousands of light years. It makes no logical sense why the galaxy should care about the black hole. But we see this coevolution happening. So we know something's going on. What's causing it? Well, it's got to be something that affects the galaxy and the black hole at the same time. And so for many years, it was thought that mergers were the driving cause. So I'm showing a video here from simulations that's two galaxies merging. You'll notice as they merge that they form a central bulge. That will become important later. And as we've got these galaxies merging, we're redistributing the angular momentum. There's material flying everywhere. It can be accreted onto the black hole and trigger an AGN. And we do see some subcategories of AGN predominantly hosted in merging galaxies, such as radio-loud red quasars, as shown by Urusha et al. 08 and Glickman et al. 15. But it turns out mergers are not the only way in which we can host AGN. So disk-dominated galaxies allow us to look at the merger-free regime because they grow through this kind of secular accretion of gas from their wider environment. And this means it's not disturbing the disk. And actually simulations such as that by Martin et al. 2013 showed that wherever we have a low bulge to total ratio, so very, very little bulge component, then the fraction of baryons that are due to major mergers, so greater than 1 to the 10 ratio, is very, very low. Now, just because we have a high bulge to total ratio, it doesn't mean we've necessarily been through mergers. So this is a one-way relationship, but it means we can use disk-dominated galaxies to isolate the merger-free regime, although we are missing some of our merger-free galaxies. So if we see AGN, these black holes accreting most of their mass in disk-dominated galaxies, we know they've grown through merger-free processes. And as you've probably guessed from the title of my talk, we do observe AGN in disk-dominated galaxies. So here I'm just showing examples from Simmons et al. 2011 and 2013, but this has been shown so many times. So Shavinsky et al. 2011, Kuchevsky et al. 2012 showed this as well. We know these AGN are growing in the absence of mergers. It also turns out, not only does merger-free growth exist, it's actually the dominant process by which supermassive black holes gain their mass. So this study by Martin et al. 2018 uses horizon AGN, and they show that actually 65% or so of black hole growth since redshift 3 is due to merger-free processes. And actually, EAGLE, used by McAlpine et al. 2020, showed that this could be as high as 85%. So we know that merger-free growth exists, and we know it's the dominant cause of black hole growth. But actually, we know very little about it beyond that. So in a study by Simmons, Smethurst, and Lintott 2017, they wanted to know whether or not merger-free growth was consistent with merger-driven growth. Could it grow black holes to the same size? And the short answer is yes, mostly. It turns out the very biggest black holes do seem to need merger-driven growth, but we can comfortably grow black holes up to 10 to the 9 solar masses without the influence of mergers. And I've superimposed here the Herring and Ricks relationship, although this time using the total stellar mass instead of the bulge stellar mass. And we can see that the relationship that Simmons et al. Found compared to the Herring and Ricks relationship are pretty much indistinguishable. The slight offset we see is likely just due to the different ways the two samples measured black hole mass. But in general, merger-free growth is consistent with merger-driven growth. But this is only one study, and also Brooke Simmons is my supervisor, so I'm probably biased. So let's have a look at some more studies. And oh no, the picture got nasty. So I've added on here some studies by Rines et al. And Bernard et al. And we can see that we're now getting very different results. So my colleague, Matthew Thorne, is working on sort of reconciling all these results together. And he's shown through simulations, paying careful attention to the selection function, that actually all three of these samples are consistent with being drawn from the same underlying sample. And actually the bolometric luminosity is a better determinant of whether something lies on this relationship. And Matt is currently writing up his work. So hopefully we should see this in the next few months in published. Okay, so that's really what we know about merger-free growth so far. We know it's happening. We don't really know how. And this is where my work comes in. So I'm looking at whether or not large-scale bars are a feasible mechanism of triggering AGN, fueling AGN. And studies have done this before. So here I'm showing work by Silva Lima et al. 2022. And they showed that the AGN fraction is higher in barred galaxies in the blue than in a comparison sample of unbarred. But look at these error bars. They are overlapping in pretty much every case. So it's hinting at this kind of tantalizing result. There might be something there, but we can't be too certain. And this is in agreement with studies such as Galloway et al. 2015, but studies such as Chung et al. 2013, Golding 2017, don't find any link at all. So is there something happening? Is there not? And the reason it's so challenging to disentangle this link is partially because of selection effects. So there's plenty of galaxy parameters that seem to correlate with both bar and AGN presence. And we need to separate those out if we want to isolate a relationship. There's also the problem that bars are very long-lived structures. AGN, not so much. So if we see a barred galaxy without an AGN, it could be that there was previously an AGN in that galaxy, but this AGN has since switched off. So we observe it as no AGN. So my work starts with the same parent sample that was used in Simmons et al. 2017. So we know coevolution is happening in these galaxies. So these are luminous type 1 AGN, which were selected through catalogs such as WISE, 2MASS, and ROSAT, hosted in unambiguously disk-dominated galaxies confirmed with SDSS photometry. And we know, like I say, that we're going to need to control for some external parameters before we can isolate the effect of bars. So here's just a quick thing showing that bars correlate with color. Unfortunately, so does AGN presence. So we're going to need to control for things. I'm going to control for star formation rate and stellar mass. These are the two main things that are going to be my problems. And given that these are all imaged with SDSS, a lot of them have SDSS fiber spectrum. So a fiber spectrum is, we place an aperture over the center of the galaxy and we collapse down all that light into a one-dimensional spectrum. And this is fine for many, many things, but it's not quite fine for AGN, because you can see the bright AGN in the middle is contaminating the light from the host galaxy, which makes disentangling them incredibly challenging. And actually something like long slit spectra are much easier to work with. So we got long slit spectra for 56 galaxies in this sample. And the bonus of long slit spectrum is we observe this bit I'm showing here in between the red lines, and then we can place an aperture over just a part of it and collapse just that bit down into a one-dimensional spectrum. So here I could take just the AGN spectrum, or I could place another aperture here and just get the galaxy spectrum. And this means I've got two spectra from one exposure. And we can see that the AGN and the galaxy spectra are very different. And it means that we can significantly easier subtract the AGN contamination. So if you're not familiar with spectral fits, if it's not something you see very often, this might look messy and complicated. But really, the black line is the reduced spectrum with the errors in grey. The different Gaussians that you see along the bottom are the various components. So in the AGN, we've got H alpha, nitrogen 2, and a broad H alpha component. Remember, we have those broad emission lines when it's type 1. And in the galaxy, we don't have those broad emission lines. And I'm imaging here over H alpha because this will allow me to obtain the star formation rate. Once you've got H alpha flux, it's very simple to then obtain star formation rate. Awesome, so I've now got star formation rate for all my sample, but I don't have stellar mass yet. And we wanted to just lift the stellar masses from the SDSS spectra, but as I mentioned before, that was going to be a problem. But what we could do instead is we had HST images of a number of these galaxies from a snapshot program, and we could use these images to help us out. So when we're looking at SDSS photometry, the PSF, the point spread function of SDSS, is very high just because it's on the ground. So these AGN that are point sources in the middle actually look like they're contributing a lot more to the overall light than they are in reality. And when we image these same 9 galaxies in Hubble, they look so much nicer. And our point source is much more accurately represented in these images. So my colleague, Matt Fahy, for his master's project, he fit all of these galaxies with GalFit, photometric fitting software. And GalFit will tell you the magnitude of the PSF, and it will tell you the magnitude of the system as a whole. So if we assume that the PSF is entirely due to AGN activity, we now know the magnitude of the AGN, and we know the magnitude of the source as a whole. So we can work out the fraction of flux that is just due to the AGN, and conversely, the fraction of flux that is just due to the galaxy. Excellent. We can then apply these fractions to our SDSS magnitudes. Run them through to obtain the stellar mass, and away we go. But as I mentioned, we don't have HST images for our whole sample. For some, we only have SDSS. And we can't apply this same method to our work with SDSS because the PSF is simply too large. We would overestimate the AGN contribution. So I calculated the fraction of the flux due to the PSF, FPSF, for HST and for SDSS in the blue for the galaxies that I had both of these data sets for. And you can see in every case in the blue, SDSS overestimates the contribution of the PSF to the flux as a whole. So I could fit a running median to this data and make an estimate at the fractions, the fractional PSFs that I could then use to apply to the Sloan magnitudes and obtain stellar mass that way. We're just working with massive error bars. That's okay, it happens in observations. So okay, in the red now I've got star formation rates and stellar masses for my active sample. And I need a comparison sample of inactive disks, which I take from Galaxy Zoo 2. So those are shown in the blue. Where I've got arrows in my data points, that's where I can only obtain upper limits on the star formation rate. And we can immediately see that the inactive and the AGN hosts lie at a different sort of regime. So the AGN hosts, you immediately notice, are at a higher stellar mass. But this is likely a selection effect, because if we're looking at the most luminous black holes, if everything is Eddington luminous, that means we're likely looking at the most massive black holes, and we already know those lie in the most massive galaxies. So that pushes the mass of our AGN hosts up. Not only that, but we want unambiguously disk-dominated galaxies, which means the disk has to be big enough that we can see it beneath the light of the AGN. So we're looking at bigger disks. So we know we're going to need to control for stellar mass. But the star formation rate is also interesting here, because the literature doesn't really agree on what AGN and star formation rate, like what the interplay is. So I put my studies on bars on hold, and I investigated just the star formation rate. So I controlled for stellar mass and looked at the distribution of star formation rate in active and inactive galaxies. And we can see, so I used KS tests, which test whether or not two samples are consistent with being drawn from the same parent sample. Where we get a high p-value, then, which is what we've got here, then the two samples are consistent with being drawn from the same parent sample. So this work seems to show that the star formation rate with AGN hosts is indistinguishable from that in inactive galaxies. And this could be because by the time I'd gotten rid of my galaxies where I only had upper limits, I only had 34 AGN, which isn't ideal. But it could also be because of outflows. So in a pilot study coordinated by Rebecca Smethurst, we got Keck time for 4 of these galaxies. So if you look at the middle row, these are ionization plots. So where we've got red, it's indicative of ionization due to star formation. And where we've got blue, it's indicative of ionization due to AGN activity. And we can see that the AGN activity reaches the full extent of the galaxy in each of the 4 cases. So outflows can affect the whole galaxy. But what does this have to do with star formation rate? Well, as we've got an outflow moving through a galaxy, at the front of the outflow, we're compressing cold gas. Where we compress cold gas, it gets denser, we get star formation. But in the wake of the outflow, we've blown away all of this gas. No gas means no stars. So this could explain why my distribution of star formation rate has both really high values and relatively low. And high resolution IFU data for a greater sample would help us to disentangle this relationship further. Okay, so back to my original aim of analysing the effects of large-scale bars. We know we need to control for star formation rate and stellar mass. And we do that, and then we look at the bar fraction in each of these samples. So in my AGN hosts, I found a bar fraction of 59 plus minus 8%, and in the inactive hosts, a bar fraction of 44 plus minus 8%. So it looks like the AGN hosts have a marginally higher bar fraction, but I've run into the same problem that previous studies have, where if we look at these error bars, they are massive. So we're hinting at this potential results, but we really can't say anything with any statistical confidence. And really, this is scientific evidence that you should give me more data. So I know a lot of astronomy problems pose give me data as the solution to everything. But the problem here is a little bit more complicated. AGN are not particularly common objects, and nor are completely disk-dominated galaxies, which we need to rule out the merger-free history. So finding them together is incredibly challenging. Now, they're not so rare that the next generation of surveys, such as Euclid and LSST, won't help us make dramatic jumps in statistical robustness. But obviously those are not yet online. I can't wait until I give this talk and I can say, and Euclid data is online. So in the meantime, we turn to simulations. So in work led by my colleagues, Rebecca Smethurst and Ricardo Beckman, we used Horizon AGM to analyze the difference between merger-driven and merger-freely grown black holes. So the bonus of using simulations is more data. It also means that we don't need completely disk-dominated galaxies. We can just track the merger history of our galaxies. So we divide them into no major mergers since redshift 2 and at least 3 mergers. And I'm showing here the velocity dispersion relationship I showed earlier from the Cormandy and Ho review. And we can see that both merger-driven and merger-free black holes happily lie on this relationship. Again, it seems that we do need mergers to grow black holes to the most massive sizes, but they're all consistent with the same underlying relationship. The interesting thing we noticed as well was that the black hole mass seems to be independent of the bulge to total mass ratio. And these similarities are quite surprising because in a companion paper, also by Beckman and Smethurst, we looked at the spin of these black holes. So in purple, I'm showing the merger-free, and in gray, I'm showing the merger-driven. And on the x-axis, I'm showing the alignment of the spin of the black hole to the host galaxy. So where we've got a spin value of 1, that is the two are completely aligned. And we can see that merger-freely grown black holes are significantly more likely to be more aligned with their host galaxy in their spin. And this is a strong result that we see to greater than 5 sigma. And when we combine this with the fact that the spin values of these black holes is also higher, so they're spinning faster, and we know that feedback and spin seem to be linked. You can check out DeVay et al. 2019, who used SIMBA simulations to investigate the link between spin and feedback. But so where we've got merger-freely grown black holes, they are more aligned with their host galaxies and spinning faster. And this means that the AGN, if there is one, is more likely to be in radio feedback rather than quasar feedback. I think I've got that the right way around, but yeah. So could it be something to do with the fact that it's radio feedback that's driving this coevolution? So we currently have many open questions that are all basically, please give me more data. So what are our next steps? Well, I got more data. So DESI legacy surveys contain 8.7 million galaxies. And my colleague, Mike Walmsley, who's just started a job at Toronto, used machine learning to identify the morphology of all of these galaxies in a way very similar to that of Galaxy Zoo. And we couldn't use traditional citizen science methods for 8.7 million galaxies because at current rates, it would take about 200 years. And I'm really hoping to retire at some point in the next 200 years. So excellent, I've now got morphologies for 8.7 million galaxies. So I can select disk-dominated galaxies from that sample. Now, unfortunately, I do still need to identify whether or not they host an AGM. And for that, I use SDSS emission lines, which does limit my sample size. So I use BPT diagrams to select AGM. So I am going to go through these in a little bit of detail, but not completely. If you have more questions, you can absolutely come find me afterwards. But our first step was with the 4 emission lines on this left-handmost plot. So N2, H alpha, O3, and H beta. We wanted to make sure our source had a signal to noise of at least 3 in each of these emission lines to make sure that there was enough emission that we could classify it. If it didn't make it onto that first plot, we then said, okay, it's undetermined, and I'll come back to what that means in a minute. But if it had a reasonable enough signal to noise, we then used a hierarchical combination of these three plots, so that's factoring in S2 and O1, to distinguish between star-forming AGN liner, which is low ionization nuclear emission region, and composite, which is a mix of star formation and AGN activity. So every galaxy that had both DESI morphology or DESI legacy morphology and SDSS photometry now was classified as one of these 5 things. So I said I'd come back to what undetermined means. Given that I'm only looking at disk galaxies, and given this is just galaxies without much emission, it's likely we're looking at red spirals. And I visually looked at a number of these to confirm. So yeah, undetermined is almost definitely red spirals. So I kept the galaxies classified as AGN, and I also kept star forming and red spirals so that I could draw some comparisons. And we used DESI to divide these disk-dominated galaxies into strongly barred, weakly barred, and unbarred. And this gave me a sample with 3,800 AGN, which is a little bit more than 34. So I now have data. So we then controlled for mass and color. Color is kind of a proxy for star formation rate. And we looked at the different activity levels in each of the bar categories. So where we've got unbarred, weakly barred, and strong barred, we saw how many were AGN in the red, star forming in the blue, and undetermined, so red spirals, in the grey or navy blue, depending on your eyesight. And we can see immediately looking here that strong barred galaxies are likely to host AGN. And we now know this with a lot more statistical robustness, because look at those error bars. We're finally getting statistical clarity here. And this was really exciting. So we then moved on to comparing AGN just to star forming or just to undetermined to see if we could notice some subtleties. And we actually got some really interesting subtleties out here. So where we're comparing AGN to star forming galaxies, strongly barred are clearly the most likely to host AGN, but weakly barred are still significantly more likely than unbarred to host an AGN. But where we're comparing AGN hosts to these red spirals, these quenched galaxies, strong bars are driving this correlation, and weakly barred and unbarred galaxies are about as equally likely as each other to host an AGN. So what is causing this disparity between the effectiveness of weak bars hosting AGN? We don't know. So there's a number of reasons this could be. So Jean 2023 showed that weakly barred and strongly barred galaxies appear to have different formation mechanisms. So maybe it's a formation mechanism, whatever forms the bar is triggering the AGN, and we're just looking at the bar as a proxy. There are some studies very recently showing that AGN activity can strengthen any bar that is present. Could that be something to do with it? The main difference between star-forming galaxies and red and dead galaxies is the gas content. So could it be that weakly barred galaxies are less efficient at funneling gas down to the central kiloparsec or so? And in the star-forming galaxies, where there's plenty of this gas, weakly barred galaxies can get some down. But where we're comparing to our quenched spirals, there's simply not enough gas for weakly barred galaxies to be able to drive this gas down, and it relies on strong bars. So there's many, many questions here. But the first one we wanted to look at was, is this consistent across color mass space? So this looks like a lot going on in this plot, and there is, but don't worry, I'm going to walk you through it. So on the x-axis, we've got the stellar mass. On the y-axis, we've got the color. So I'm comparing two activity categories and two bar categories. So AGN versus star forming. And here I'm comparing strong bars with no bars. So in the contours is all of my AGN and star forming disk galaxies. In the histogram, I am showing the difference between the AGN fraction in the strong bars and the AGN fraction in unbarred galaxies. So we're also only doing that where there's at least 10 AGN in a bin, so otherwise it's really noisy. So if I lost you a bit there, if it's green, strong bars are more likely to host an AGN. If it's purple, unbarred galaxies are more likely to host an AGN. And there is no purple. So we thought, well, this might just be a result of the binning. It could be we're binning it in a way that's doing this. So we tried it again. And we tried it again. And we tried it again. And every time it's coming up that strong bars are completely more likely to host AGN than unbarred galaxies. And so for every combination of binning, we did this from 5 to 17 bins in each direction. So that's 169 binning combinations. We obtained the average difference in the fractions. So here that would be 0.2-ish. And we obtained the fraction of bins where the stronger bar category was dominant. So here that would be 100%. And we did this for strong versus unbarred, weak versus unbarred, and strong versus weak barred. And we assume that what's actually happening is there's a true value of the difference between the fractions that we're sampling around, which will give us a nice Gaussian shape, which we get. So this dot dashed line indicates what we would expect if there was no difference between star forming and between strong and weak bars hosting AGN. And the more rightward of the line of equivalence our distribution is, the more likely it is that the stronger bar category is more likely to host an AGN. So we can see very quickly that in every case, the stronger category is more likely to host an AGN in the unbarred category. So that second plot is where it's like the fraction of bins where the stronger bar category is dominant. So this is very indicative that at all colors and masses, strongly barred galaxies are more likely to host an AGN than weakly barred, which are more likely than unbarred, comparing AGN to star forming. And we did this for AGN versus red spirals as well. And again, we're noticing that strong bars are driving the correlation, but this helps us untangle a little bit more of the difference between the weak and the unbarred galaxies. So when we look at it across color mass space like this, we notice that weak bars are maybe slightly better at hosting an AGN than their unbarred counterparts, but it's very, very slight. And actually the distributions are very close to zero for weak and unbarred. And it really is strongly barred galaxies driving this correlation. Now, this result is incredibly statistically robust, and it means we can kind of put a pin in the do bars fuel AGN discussion, because this work indicates yes. And this means there are so many open questions. I have more questions finishing this work than I do when I started. So we only used optical AGN here. What happens if we use X-ray selected AGN or infrared selected AGN? What happens at higher redshifts, where we know that the AGN fraction increases, but the bar fraction decreases? What's happening there? What's the black hole accretion rate looking like in the difference between strong and weak bars? What's the mass of the black hole looking like in the difference between strong and weak bars? There are so many open questions, but unfortunately I have a thesis to write. So I'm being told I have to stop doing the research and write it down. So I will leave you with my key take-home points. So first of all, merger-free black hole growth is poorly understood as a whole. AGN host galaxies are marginally more likely to host a bar than inactive galaxies. But when we have more data, when we compare AGN hosts to star-forming galaxies, strongly barred are more likely than weakly barred, which are more likely than unbarred to host an AGN. But when we compare to quiescent galaxies, our red spirals, strongly barred galaxies are driving the correlation, and weakly barred and unbarred are about as likely as each other. And really further work and simulations will help us to disentangle this relationships going on here. And larger surveys coming out will help us even further to isolate this difference between weak and unbarred galaxies. And we can do so much with this work. We don't know where to start. Thank you very, very much for listening to me. I'm happy to take any questions.
Very nice, very nice. Yes, we have time for questions.
So I'm wondering how much of your conclusions are affected by this issue that you mentioned, that the AGN could be obscured, so the assumption that, you know, what the time scale of this creation, how many or how fraction of the light is obscured, is this something that will impact your conclusions or not?
So it will, if we are essentially missing some AGN, this will impact our conclusions, but it will actually strengthen our conclusions. So it's quite likely where we've got a strong bar that we could be missing some AGN activity. That actually means our AGN fraction is even higher in strong bars, and that strengthens our conclusion. So we're not overly worried about it. The timescale difference, the fact that bars are much longer lived than AGN, I think, again, that would strengthen our conclusion because it would mean that we're missing some AGN in our barred galaxies. So it is definitely something that to identify quantitatively we need to consider, but qualitatively to know that these differences are real, it's not a major concern, but it is something I want to look at further.
I mean, I was thinking, for example, could it be that the fraction of AGN is the same, but what the bar is doing is somehow making that activity more frequent or something like this. So the AGN is there, but you don't see it. When you have a bar, you don't see it as often as when you have a bar.
You mean that the bar is triggering?
Yeah, it's triggering activity. Rather than
Contrast is
Exactly.
supplying the
Yeah.
record.
So it could be that these phases are happening. Simulations will really help us to understand more of this. The problem is AGN feedback is not currently well understood enough for us to be able to simulate it on large scales. We can do it sort of individual galaxies. And that's a problem we're having with bars and simulations as well, is that we can do it for individual galaxies, but on a large scale, we can't really mimic what we see. There is actually work going on at Zurich. One of their PhD students is looking to improve on the barredness of simulations. I'm really hoping she gets somewhere with it because then I can use that. So there is a lot of work that needs to be done with simulations that we can't quite do yet because we don't understand enough about the underlying physics. Yeah. Yep.
Hello, thank you very much. That was a very well, presented and very clear. I was wondering about the stellar mass and star mass array indicator. Because one problem is that given AGN activity or non-AGN activity, this could dominate a lot in the colors, and you have very indicators that are used. So here, for example, the stellar mass, how is it computed?
So the stellar mass, we use something at all 2004.
Band magnitude?
UNR.
Hmm.
UNR band. It's not, might be Brinkley at all 2004, who show a relationship between stellar mass and the colors. And this is why we used the Hubble images to try and counteract for that. Obviously, the higher resolution we're using, the better, because that allows us to subtract the AGN component. So here, which band did I do this in? This is showing it in I band, not U or R, because that was the band we had for GalFit. So we are making an assumption that this is like the AGN to galaxy fraction is the same in the I band as it is in the U band and the R band, which given their proximity, seems like a very reasonable assumption. So it was a lot of subtracting out the stellar mass. Coming up with this method took some time. The star formation rates. So coming to here, so where I started extracting the galaxy spectrum, I made sure I knew how far away it started from the center. The PSF is Gaussian, so I knew that if I started 2 sigma away from the PSF, there was going to be 2.5, half of 5% contamination. If I started 1 sigma away, there'd be 16% contamination. 3 sigma away, there'd be I can't do maths that quickly in my head, 0.1% or something, depending on Gaussian standard deviations. So when we then had these, we knew that any broad component would be due to AGM, but I then say I knew the contamination was going to be 2.5%. I would take 2.5% of the AGN flux away from the galaxy flux at each wavelength. It was a very painful process, but we got there. And that's why we have so many, come on, not that one, this one. So many of our star formation rates, we only have upper limits. Because by the time we've done all that AGN subtraction, a lot of the time it doesn't look like we've got any signal left. For further analysis, we actually removed our galaxies with upper limits because KS tests showed that the sample where we had actual values of star formation rate and the sample we had upper limits on weren't consistent with being drawn from the same parent sample, so our upper limits are not even a little bit accurate. So we took them out for any further analysis.
So the substance rates are H alpha.
Yeah.
Okay.
Yes.
And this goes to the another discussion. For example, if someone told me that there is correlation with substance rate, I wouldn't be surprised because substance rate correlates with stellar mass.
Yeah.
So if the mass of the black hole correlates with the total mass, it should correlate with substance rate.
It should.
So, but I would be interested to see, like I don't know, a plot of mass of black hole or in agent presence, of course, mass of black hole over total mass versus substance rate. If excess in substance rate or in specific substance rate, there's something extra that this large sample might be able to see that.
That would be
in a city thing of more star forming, more agent potency, say, okay, so there might be more masses in a beam of masses. You have a distribution of masses as well, so you have a distribution of mass rate. So this correlation is already in and contributing to it. However, if you do this kind of try to find the excess in these kind of correlations and how it correlates with specific supplements or supplements rate, it might give a more separated sample that shouldn't be there.
That makes a lot of sense. I'm going to make that plot when I've got 10 hours on the train tomorrow. I would absolutely love to. Can I get your email at some point? So if I manage to make it, I can submit.
We'll talk soon.
We will, yes. Fun. Because yeah, the whole problem with this sample that well, the whole paper and the full write-up is in my paper that came out in April, I think. I should really know the month it came out. The whole problem is the sample is too small. So the whole paper basically functions as please give me access to data. Talking with Mara earlier, you've got some really exciting data coming up with DESI that I really want to use. That's going to really help as well. And if we can then get stellar masses from that, expand to a larger sample, I can do some really fun statistics. But yes, I will definitely be interested in sort of having a further discussion on that.
Time for another question. Yes.
Yeah, so thank you for a nice talk. I have like millions of questions, but I can pick up probably only one, and I will present the rest for our meeting later. But maybe I will pick up the question which is more broad and can be used also for others. So can you go back to the plot of the fraction of AGN on the images you compared HST with SDSS. It's the previous one, I suppose.
This one or
About the plot of the fraction. Of
Yeah.
Oh, exactly. I really like it because it reveals how important is accounting for AGN, and especially for people who are not only interested in AGN but also galaxies and studying the properties that we have to account, especially on SDSS. We can see that the fraction is really large. And I wonder, how did you decompose the HSD images and why the errors are so large at some point?
so for the I'm going to start with the latter part there, why the errors are so large. So laser pointer time. So the red points are where we don't have actual HST values. We're using SCSS to make an attempt. Because of the large spread in the real values in the blue, that's where the large errors come from. So down here, where the spread is like this, that's where our errors are from. Up here, they're massive because so in this bin, we've got such a range of FPSF for HST. I'd love to be able to get the errors down somehow, but that wouldn't be accurate science at the moment. This is where I'm excited for Euclid, because HST-ish resolution on a massive scale, I can get better estimates here, which will be amazing. Decomposing the galaxies, or the abstracting the AGN component. So that work was conducted by Matt Fahey. The paper is currently in prep because he's left academia, sadly. Have you used Galfit before?
I know Galactic,
Yeah.
I didn't use it. So I know.
I've also not used it. Matt did. And he sat next to me for 3 months complaining about it. So it essentially, if I remember this right, it fits a 2D Gaussian PSF to get the point source. It then fits with various ICE-CSIC parameters. I think he did up to 5 additional components. So in some cases you could get like where there was maybe like a small bulge, or you could get the whole disk, you could see some spiral arms and things. And then we just summed those components up to obtain the total source. If I ask Matt, I can probably give you his thesis where he'll go into it in a lot of detail, but I don't know the full ins and outs of it.
And do you know if it fits one galaxy at each time, or take into account the neighbors? So I mean that, you know, the thing that we should take into account is the environment of these galaxies, right? So Galactic is very sensitive for also this. So I wonder if this is somehow taken into account.
So he had 101 galaxies. He did it with batch fitting to start with, and then looked at the residuals. Where the residuals were nasty, he then did it manually. They were mostly nasty. He mostly ended up doing it manually. So because most of it was done manually, things you can do when you've only got 101, we could do things like make sure like this little blob wasn't included. So I'm pretty sure he did subtract out all the little things around. Yeah, with combination of batch and manual, which is not a satisfying answer.
You talked about outflows and say the AGN and inactive galaxies have similar transformation rates.
Yep.
But shouldn't be that those triggering or suppressing the star formation rate, should we see a statistical difference between
So
inactive and those?
so this is why we want high resolution IFU data. I think Becky Smethurst is submitting a Muse proposal soon. where we can hopefully track the star formation with the outflow, so we can actually look at. So let's look at this first galaxy. So at the edge of the outflow here is the star formation rate higher than, say, closer to the center. That data we don't currently have. We want it. So this is, we think, why we get the AGN hosts having both the largest star formation rate and the lowest, because these outflows are simultaneously enhancing and quenching. But we can't uncover more without more data yet. Please give me data. Thank you.
Okay, I think we can stop it here, and Izzy will be around until 3, 4 p.m.
Yeah, I can always, I have no plans this evening. I can stay as late as discussions go.
We have a group meeting afterwards, so you are all welcome to join the group meeting and discuss more. Thank you very much.
Thank you. And so, oh, I feel like I've gotten a lot more confident delivering presentations over the last 3 weeks.